Hey Finxter, what's up? It's Chris, founder of Finxter.com, and in today's video we are going to explore the Bitwise AND operator. So this is part of my my video series about all Python operators, and a small part of those operators are the Bitwise operators. So I think there are between 8 and 10. I'm not quite sure yet how many operators actually I have. Maybe I can count it quickly. So there are 1, 2, 3, 4, 5, 6. Actually, six Bitwise operators, and I'm just quickly going over all of those Bitwise operators because you will need them from time to time. You will see them sometimes. Some Python coders use them regularly. Others most coders use them seldomly. But if you are involved, like in larger code projects, and you work with other people on code projects, then you will see it from time to time that people just use the Bitwise operators for some brevity in their code, or just to write smart code. So I think it makes definitely sense to check them out. Okay, so what are the Bitwise operators? First of all, they seem quite confusing. So say, for example, you have you apply them on integer numbers. So say you have an integer number 10 and 8. So this one is a Bitwise operator, the AND operator. It's an overloaded operator, so if you apply this operator to sets, it has a different meaning. It means intersection for sets, but on integer numbers, it means perform Bitwise AND operation. And now what does it mean to perform Bitwise AND operation, and why is it 8? Why is the result 8 if you have 10 and 8? It doesn't seem to be logical. So for example, if you have 10 and 8, this now is a logical AND operator, and I have already addressed the logical AND operator in a previous video, and now maybe you can already figure out the result of this operator. Here we basically, each integer number has an associated truth value, and actually all integers, even negative integers, are true per default, except integer 0. Integer 0 is considered to be false, so the implicit truth value of integer 0 is false. So this one is a true value, so therefore it simply returns the second operand, because the second operand for the logical AND operation, the second operand determines whether the whole expression is true or not, right? So it simply returns the second operand, which is 8. So this is the result of this AND operation. So if you perform 10 and 8, it seems to be similar, right? It seems to be it seems to work the same way. But now let's have more complicated examples. Say, so what is a good example? 32 and 16. Okay, now here the result is 0. So let's consider 32 and 16, and again, like expectedly, we get 16 as a result. As in the previous setting here, we get the second operand as a result. But why is now 32 and 16, so the Bitwise AND operator, 16 0? So this is quite confusing for many people. Okay, so let's dive right into the AND operator. I will give a bit of context and theoretical understanding of binary numbers as well, binary representation in Python, and so that you will figure it out. Okay, so first of all, so like the Bitwise AND operator, first of all, we will look at positive integer numbers, because it's much simpler for positive integer numbers, in my opinion, and then we will dive into the representation of negative integer numbers and how the Bitwise operator works on negative integer numbers. Okay, so on positive integer numbers, you know, each integer is represented by a bit, by a stream of bits, right? For example, the value 32, I can give you a table showcasing this. So we have, so here we had values, decimal values 32 and 16, so integer values 32 and 16. And here is a table. In this table, you see this one here is the bit representation, or the binary number of the value 32. Okay, so we have 1 0 0 0 0 0. Okay, so why is that? Because this one is 2 to the power of 0, right? This position indicates, so in a binary number, this position indicates how many times we have 2 to the power of 0. So we have 0 times 2 to the power of 0, 0 times 1, plus 0 times 2 to the power of 1, 0 times 2 to the power of 2, 0 times 2 to the power of 3, 0 times 2 to the power of 4, and 1 times 2 to the power of 5. And 2 to the power of 5 is 2 times 2 times 2 times 2 times 2, which is 32, right? So that's why we have, like, basically this is our binary representation of the number 32. For the second operand, this one here was 2 to the power of 4. So we have 1 times 2 to the power of 4 and zeroed out everything else, which means that we have 16 here. So these are our 2 operands, right? And now if we perform the AND operation, the bitwise AND operations, we go for each position I, we basically perform the logical AND operation. So we don't perform the logical AND operation on the whole integer numbers as done here in this example or in this example. Rather, we perform it on the bit positions of these numbers. Okay, so and you can see here we have we, for example, perform logical AND on these 2 instances, and here we have 1 and 0, and basically logical AND is 0, right? Because it would only be 1 if both operands actually are 1 already. Okay, so and in this case, like at least one operand is 0 or both operands is are 0, which this means that the logical AND of those 2 bits is 0 as well. Okay, so we have basically zeros everywhere because there's no instance where we have a 1 at all in all places, right? So therefore, the result of 32 bitwise AND 16 is 0, right? Because we have just, I mean, the bitwise logical AND operation is 0 as well. Okay, let's have a look at another example that is a bit more expressive maybe. So, which is like we can use 31 and 15, right? 31 and 15. So here again we have result 15 and 31 bitwise and 15. We have the result 15 as well. So why is that now? This is similar to this example here. We now have the same results of the bitwise AND operation and logical AND. Why is that? Yeah, because just again go over the numbers. So we have the first operand here. We need to represent 31. The number 31, which is 1, 1, 1, 1, 1. Why is that? Because we have 1 plus 2 is 3, plus 3 is 6, plus 4 is it 4? Yes, plus 4 is 10, plus, actually there's one missing, right? Plus, no, this is not, I think this is not right. There should be one additional position 1. Right? Because we have, like, if we have 32, if this is 32 representation, then 0, 1, 1, 1, 1, 1 would be, so with 5 ones would be the binary number, would be the decimal number 31. So basically, if you reduce this by 1, we get the result 0, 1, 1, 1, 1, 1. So we have, okay, no, it should still work, sorry about that. Okay, so we have 31 like this. Okay, so we have here 16 plus 8 is 24. Okay, now, sorry, I get it. So we have 16 plus 8 is 24, plus 4 is 28. Sorry about that. Then we have 30 and 31. Okay, so it works out. Okay, and the second operand is 15, which is like everything from the above example, but except the 16 position. So we add them together with the bitwise AND operation, and we obtain the value 15 again, right? Because only for those positions we have both operands are actually 1. Okay, so and this one is basically the second operand, right? 15. Okay, so that's how the bitwise AND operation works in its most basic case. But we will have some more examples maybe. I think it makes sense to actually look at discuss the negative integers on if you have negative binaries, because now it may look strange. So for example, if you do something like minus, say, 10 and minus 2, something like this, the result is minus 10, and it's not like obvious why is this the case, right? We can now have a positive here, so it's not like intuitively clear how this works. So actually, let's maybe first discuss what does it even, how is minus 10 represented as a complementary binary number. So in say you have 8 bits and your to represent a decimal number, right? So we have 1, 2, 3, 4, 5, 6, 7, 8. So these are the bits that can be represented in Python, right? So now we can have we can like represent, as you know, binary numbers. So for example, this one would represent binary 1. This one would represent binary or decimal 3 as a binary number. This one would represent binary 7, and so on. Okay, 7, we want to increase it by 1, which means that we add 1 here, becomes 0, becomes 0, increase it by 1, but then we need to add the 1 here. Okay, so this is like the standard representation of the binary numbers. And you see, like to represent with 8 bits, we can basically represent a lot of different binary numbers up to this number 4, 5, 6, 7, 8. So up to this number we can represent all different binary numbers. And now it's just per convention Python uses for 8 bits, it uses the first bit as the sign of the number, and the remaining 7 bits it uses as the representation of the number itself. Okay, so if the first bit has a sign 0, it basically means it is a positive number. If the first bit has a sign 1, this means it is a negative number. And now I will discuss how negative numbers are actually represented. And the strategy is quite simple. So say you have you want to represent x equal -1. So this is a number you want to represent as a binary or complementary binary as a negative bit string. So now you would do the following strategy. I would just write it loosely here in the Python shell to explain it to you. So first of all, you would calculate the positive number that you want to represent as negative number, which is 1, so the positive part, and you would simply calculate -1. So you simply reduce it by -1, and the result of this is 0. Okay, and now you use this 0, so the value 0, to represent as a binary number by actually flipping all the bits. And remember, you have 8 bits. So basically you first represent it as a binary number. So you have 4, 5, 6, 7, 8. So this is what you're first doing. And then you just flip all bits. 1, 2, 3, 4, 5, 6, 7, 8. So this one would be the final representation of your binary number -1. And don't worry if this doesn't make sense yet. I will just give you another example and then you will get it. Okay, so say we want to represent the negative integer number 10. Again, we are taking this decimal part 10, the positive part, represented as reduce it by 1. So we basically get, let's just replace it. So we calculate 10 minus 1, which is 9. So now we have 9. We need to represent 9 as a binary number with 8 bits. So representing it as a binary number with 8 bits is 0, 0, 0, 1, 0, 0, 1. So this is our representation 9 with 8 bits. And now we invert all bits, which we obtain, which leads us to this number. And you see the first bit has value 1, so therefore it is a negative complementary binary representation. Okay, so this is how it works actually. So maybe let's have another example just to make sure that you get this. So say we want to represent -11. Again, we take the positive part 11, we reduce it by 1, which gets us the decimal number 10. Now we need to represent the decimal number 10 as a binary number with 8 bits. So we have 0, 0, 0, 0, 1, 0, 1, 0. So this is a binary representation of my decimal 10. And now we flip all bits. So we get 1, 1, 1, 1, 0, 1, 0, 1. And this is my number negative 10, so -10. This is my binary or complementary binary, it is called, for my decimal number 10. Okay, so this is how you can actually represent bitwise how you can represent negative integers as bit sequences, right? And you need this, of course, to perform the bitwise AND operation on negative numbers. And we will now have we will see a couple of examples. Maybe let's just open up this table which I have prepared. So say you have, let's make this a bit. Okay, so here this one. So here we have say integer 0 and -1. So we have two operands, 0 and -1, two integer numbers. And now we first represent both in binary form. So 0 is represented with 8 bits, 8 0 bits, and y is represented as 8 1 bits. And you have seen this in the previous example here. I have shown you how we can actually calculate this. So we take the part 1, the positive part of the integer, and reduce it by 1, so we get 0, and then we represent this as a binary number and flip all bits, so we get this one as our binary representation. And now actually we just perform bitwise AND operation, right? So we check 1 against 0, which is the result of this bitwise AND operation is 0. We get 1 with 0 and so on. So we actually, for all positions, we compare 1 and so we perform x and y. So and x and y in this case being just the positions of the numbers. And if you perform bitwise AND operations this way, we actually get the number 0 and 0 0 0 0 0 0 0, and by converting it to an integer numbers we get the result 0 as well. And okay, so let's repeat the same procedure for the two numbers, input numbers 0 and -3. So these are now the integer values. Now the binary representations are given here. So again we have 0, a bunch of zeros for the first operand, and this binary number, it's a negative number. You see it because the first bit, the sign is 1, and we have obtained this simply by again taking the positive part, reducing it by 1. So we have the the intermediate result of 2. So now we represent 2 as a positive binary number with 0 0 0 0 0 and so on. 1 0, and then we flip all bits. So we have, instead of 0 0 0, we have 1 1 1 1 1 and so on. Yeah, so the only not flipped bit is this one, which was positive in the previous step of this computation. Okay, so I'm not keep repeating now how we can represent negative numbers as binary strings. I would just assume that you have figured it out. Otherwise, you can go ahead and restart the video and really try to figure this out. Try to take this home from this video, how you can actually represent negative decimal integer numbers as binary numbers to perform this bitwise operation. This is really important, and it will come up again and again in your coding career. Okay, so and then we perform bitwise AND operation and get the same result 0 because our second operand is just 0. Okay, so if one of the operands is the first operand is 0, so if one of the operands is 0, then of course the AND operation will always return 0. And if you have, for example, two negative integers, -3 and -5, we can represent with those two bit strings. And if you perform the bitwise AND comparisons, we obtain this nice binary number. We have 1 1 1 1 1 0 0 1, and we if we just convert this using our strategy, we obtain the result -7. Okay, so let's have a look at those examples in your Python shell, actually to see whether we were right. So first of all, we have 0 and -1. Here we got the result 0. If because actually performing bitwise AND with a number that is just a bunch of zeros will always be 0. So we can basically have arbitrary large numbers here. They will just always be 0, right? And we can have negative numbers on both sides, like we had the example -3 and -5, and the result was -7, and this is indeed the case. Okay, so this is what happens under the hood. It actually converts those numbers to the binary representations, and then it performs bitwise AND operation to combine them. Okay, so I think we have discussed everything. We have discussed how negative binary representation works. I think this is maybe the most important thing you can take out of this video. Then it is simple. So if you have understood this step, it is actually simple to perform the bitwise AND operation on those two operands. And we have checked out the difference between logical AND and the bitwise AND, because the logical AND, it just works on whole numbers. It just uses the fact that in Python all objects are truthy, and it just doesn't look that deeply into the integer numbers itself. So it just assumes that all integers are true, logical true, and only the 0 value is logical false, and then it just uses these statements actually to perform the AND operation using some optimizations which we have discussed in the video about the logical AND operator. Whereas the bitwise AND operator, it really dives deeply into the number, into the binary representation of the number, and then checks out for each position the difference between whether there's a difference or whether both of those numbers actually are or are set are 1. So whether both bits at certain positions are 1. In this case, we will get the bit result 1, and if at least one of those bits at a position I of your binary representation is 0, then we obtain the result of the logical AND operation 0 as well. So so it goes just much deeper into the numerical representation, or the encoding of the number, we say. So they are encoded as binary numbers. Okay, so I think it's enough in today's video. You have learned a lot, and thanks for watching this video, and see you in the next video. Bye.